So every year there is at least 2 questions based on Laplace transform. Every year, one of that is fairly easy. There are other one is somewhat hard. And if you notice Laplace transforms as such, there are like 50 odd formulas, 50 odd transforms that you'll have to know. But today what I'll do is to say, okay, at least this 10 formula is the minimal number of things you need to know, so that you have a good chance of answering one easy question. You also kind of improve your chances of answering a moderate or hard question. I'll try to simplify this as much as possible. Notice, actually, the field of probability has a lot, owes a lot to Laplace. Okay, he is one of the first pioneers of probability. He also gave this Laplace transform. The idea is always this. You have a hard problem. Okay, we have seen this many times, starting with amplitude. Have a hard problem, and we want to convert it to transform, so that the problem becomes easy. There is an easier version. There is an easier perspective. There is a footwork using which things now make sense, right? Something like that. And sometimes this is a different problem than what you started with. So ideally, you also want to know how to undo any changes you did to the original problem. Okay? So undo changes. So most transforms, most operations in mathematics will fit to this category. Laplace transform also kind of fit the same thing. So it is there to make your life easy, because the problems that you're dealing with are quite hard. If not for that tool, the problems get really hard. Okay. So this is the objective of that. And Laplace transform, Fourier transform, okay, coordinate changes, many of this kind of fit in this pattern. Okay. And Laplace transform, so we go from time domain. These are hard to see. These are hard to see. X of t, right? This is represented as a double arrow. We go to the easy frequency domain. Okay, the forward, this is Laplace transform. The reverse is this way. This is Laplace transform inverse. So what are some things that we gain out of this? So this is, first of all, this is what we refer to as things are functions of time. This is in time domain. This is S is a frequency. Okay, your S is sigma plus j omega. Okay, in fact, even this detail can wait for a moment. This is, we are going to complex frequency domain. This is a complex number, so we go to complex frequency domain. Change of coordinates, actually, change of variable. Of using t as a variable, you are using a new variable that is s. Okay, so instead of using, let's say, meters, you are using centimeters, right? You can do unit conversions, right? So instead of xyz, we can use notice r theta phi. We can do polar coordinate transformations, right? So like that, we are also going from t to s. And in the process, what happens is you get a lot of benefits. One thing being, often you are stuck with differential equations here. Differential equations. That becomes algebraic equations. Say there is a differential equation that is hard to solve. Go to this algebraic equation that are fairly, algebra, this is fairly relatively easy. This is one common use. In fact, Laplace transform, the purpose is not to convert differential equations to algebraic equations. It's a transform. It helps you with many things. This being an example. And another example is, now there is this thing called convolution that again shows up in real world again and again. And this convolution becomes a product. Convolution becomes an easy product. It's a multiplication now. This is fairly easy to deal with, right? For example, if you have your y of t, right? This is a convolution of, let's say, x of t into h of t, right? Here, this thing becomes easier now. Your y of s, just a product of these two. If you know this transform, if you know this transform, you can easily deal with it. There are multiple subsystems, things cascade, all of that gets very easy to handle. This list goes on and on. Okay? This is why we do Laplace transform. Now the question is, what is this transform? What is this transform? Definition. So again, we write this as, notice you're going from f of t, this domain, to f of s, right? This is a notation for Laplace transform. This is f of s is defined this way. F of s is integral 0 to infinity the original function f of t to e power minus st t. Now time is a dummy variable that disappears. Technically, this is also, let's put a small limit over there. Okay, this is 0 to infinity f of t e power minus st. This is the definition of Laplace transform. Often the definition itself is not useful for gate, but it helps you see things. So one is the dummy variable disappears upon integration. That we could easily see, the dummy variable disappears upon integration. Okay. Dummy variable disappears upon integration. You got a new variable, yes. Integration. This point number one. And I have also told you one way to interpret this is actually dot product. This is like a dot product. We have seen this, and I have told this, and when we did many integrals and all that, you can take a dot product between I and j, right? I and j are orthogonal. Dot product is 0. So many integrals, cos theta, sin theta, right? Many of those integrals will be 0 because this is like a dot product, right? So this is like a dot product. That is, you are trying to represent f of t using exponentials. Dot product. You are trying to represent, trying to how similar, trying to see how similar f of t is to e power minus st. How similar is to this exponential? Take any function, how similar it is to this function. For example, in Fourier transform, we check how similar things are to sinusoids, sines and cosines. Okay, let me also write that down. Okay, there's a lost theory, but that I'll kind of write down. For example, we see in Fourier transform, Fourier series, let's say, in Fourier series, we see, okay, we see or present f of t using sinusoids. So instead of sinusoids, we are using exponentials. This is, I'm giving this so that you can make the connection. In a way, Laplace transform is a generalization of Fourier series or Fourier transform. So let's quickly make a contrast. How is this function? Let's compare and contrast. Let's say cos omega t. Let's compare this function with our function of interest power minus s t. Compare and contrast. So what kind of a function is cos omega t? Describe, put that in English. What kind of a function is e power minus st? Let's also color code this. Side you got sinusoids, oscillating functions. Okay. So that go up and down and keep repeating that. How about this? That is even. Okay, sinus, there is also this function. Okay, Fourier series sin omega t is also there. I was trying to compare and contrast. So cos omega t is even, but these functions are oscillating. So what kind of a function is this? So for that we need to know what kind of, omega is real here. Omega is frequency. Need to know what is this. Yes, this is complex. This is complex. Point number one. Yes. Complex. So what? Used to have a friend. Whatever you go tell him, he'll be like, so what? So what? Right? So what? This is actually a reasonable question, right? I mean, so what? Okay. So what? Notice you can do a lot more Laplace transforms. You can do sinusoids. You can also do things that are not sinusoids. So what kind of functions? Let's look at this. E power minus st. S is complex. So e power minus sigma t into e power minus j omega t. Right? S is sigma plus j omega. We have two terms here. Can we describe the two terms in the product? Again, let me color code this. You got e power minus sigma t. Sigma is a real number. Of course, omega is a real number. And then e power consistent e power minus j omega t. So this is sine omega t cos omega t. And this is power sigma t. This thing. This is exponential. This term is exponential. This term oscillatory. Euler's identity, you all know that this is cos omega t minus j sin omega t. So this has both exponents and sinusoids. Very briefly now, what this means is you can represent this function. You can also represent this function. Function that is say decaying on the way this is also oscillating. Represent this function. Conclusion, deal with Fourier transform, you can only represent oscillating functions. So sigma is positive, this decays. Sigma is negative, this thing goes up. If omega is 0, notice you can represent this function. Exponential, that is blowing up. Okay. So here this is, here sigma is 0. Okay. Here omega is 0. Here sigma is positive. Of course, sigma omega is 0, that is no oscillation. Sigma is less than 0, so that e power sigma is a negative, let's say minus 2, e power minus of minus 2t, e power 2t, this is blowing up. Bottom line, now in addition to sinusoids, we can represent, now as in with Laplace transform, represent exponential sinusoids, and represent complex exponentials. Yes. Depending on the real part, imaginary part, we can actually represent any function. That's why we use Laplace transform. We transform repeating functions. Now functions that don't repeat, but now functions that decay, functions that blow up, all of that could be represented. It's a very powerful tool. This is also one reason why you substitute S is j omega. That is, when you set this down to 0, you get Fourier transform. It's more general. Laplace transform is more general. Okay. This is like a dot product, but what you're comparing with is a very, very wider, more beautiful class of functions. List of formula, I hate to do like blind list of formula. You need to be like some understanding. Okay. Let's know one more thing, basic exponentials. Let's look at few real exponentials. And notice this integral starts from 0. So you're only looking at functions from time t equals 0. Before time t equals 0, you're not worrying about the function. This integral starts from 0 to infinity. Okay, this is referred to as a one-sided Laplace transform. Okay, we start looking at real exponentials. I have drawn one. I have drawn two. Okay. So minus power minus a1t. 2 is also e power minus a2t. You rank a1 and a2. Rank a1 and a2. Compare. That is what is high and what is low. There is no oscillation. It's just pure decay because a1 a2 real. Can you tell me what is higher? So by this I mean rank a1 and a2. Pick two numbers, e power minus t, e power minus 2t. So if this is, which one should be e power minus t and which one should be e power minus 2t? a1, a2. Is it certainly not equal to? Is it greater than, less than? What number? What symbol should show up here? 1 and 2, for example. See if this is power minus t, and let's say does this as e power minus 2t, does that make sense? Or it should it be, this should be e power minus 2t and this should be e power t. Coefficient is bigger. A1 Isha makes a call. A1 is smaller. It is decaying slower. Indeed, A1 is small. One, the coefficient tells you how fast the function is decaying, right? So this is faster decay. That means your A2 is larger. This is faster decay. And let's also, start at a convenient point. Let's all start at 1. Okay, this is now, of course, functions of time. 0 is here. More the power, it will decay fast. Yeah. Negative tells you things are decaying. This minus tells you it's decaying. Higher the value, it decays faster. Great. Fairly simple question. So now, if I keep on increasing A2, what happens as A2 tends to infinity? What curve will I get? Coefficient tending to infinity. What will I get? Okay, decay faster, that is not that important. This coefficient goes to 0. Slower and slower decay. In the limit, what do we get? What happens if this coefficient is too small? It decays slower. It decays slower. Then where does it eventually go to? That is when the coefficient is 0, where does it go? Infinity, no, this is e power 0 into t. It will remain, it will start at just like the other functions. It will not decay. 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 It's a constant. So you get a constant. You make a the coefficient negative, it will keep on rising, right? So from positive it goes to 0, 0, negative. So minus of a negative number, that is a coefficient now will be net positive. That will go to infinity. Some of you went to that side. No, if you keep on changing it further, it will blow up. That is happening, but again we'll stop here. Notice a tends to 0, you get constant. And also we gave it a name yesterday. This is nothing but u of t. That is your u of t function. So this step function, if you're only looking at positive time, it's a special case of exponential function. Great. So now let's look at some examples of Laplace transform. If you put delta here, the function you are trying to take, this is anything into delta, okay, you get just integral becomes very 0, it becomes 1. Okay. Important Laplace transform. All the story that I was trying to build will now make sense to make this important formula easier, more memorable. Okay. So what you are trying to do is now x of t transforms as x of s. Let's look at some examples. What does delta of t transform to? Delta of t transform to. This is what we call as a spike. One thing that most of you may have to remember. delta of t transformed to, okay, remember this thing, okay, transforms to 1. That integral drastically simplifies. When you substitute f of t is delta of t, it's a spike, okay, and delta of t is not even that useful for our discussion, so I'm not going to spend a lot of time on that. U of t is important, okay. So when you substitute delta of t, this integral just becomes 1. Okay, you could remember it that way. Spike, your Laplace transform as 1. What does u of t transform to? Does u of t transform to? This most of you know, we discussed yesterday. This transforms to 1 by their call, or this is your chance to memorize it. Either you know it or this is the bare minimal thing you need to know. What does e power minus at transform to? Transforms to 1 by s plus a. See, notice technically this is s plus 0, because this is also u power t is u power minus 0t. That is going to s plus 0. I'll write it very, very small so that you see the relation between these two. Same formula. I just told you u of t is when a tends to 0, right? E power minus at is decay. U of t is when the coefficient is 0, it remains a constant. You could also see that here. What this says is, look at it thus, when s equals minus a, Laplace transform is singular. What we call as a pole, that also we don't need for for today's discussion. When the denominator goes to 0, transform is infinite. 1 by 0, that is infinite. So the transform is singular. What it says is, this is a complex organ plane. And there is a real part of s, this imaginary part of s. S equals minus a. This is now minus a is here. It's a real number. There is no imaginary number. At that location, yes, the function becomes singular. Another way to put that in simple English, so in this complex plane, which point represent e power minus at best? Is it this blue point? 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 You can ask that question. Okay. Wherever the dot product is the highest, let me again go there. Wherever the dot product and the function and e power st is the highest, that value of s represents the function best. Dot product between two functions, between f of t and e power minus st. This dot product, the similarity is highest when, for the value of s, when f of t is most similar. Okay. So you can actually test what the transform is at different points in the complex plane. That is, you can substitute different values of s and see what the similarity or what the dot product is. The dot product blows up, singular, becomes infinite. The similarity is highest at this one location. In other words, similarity is highest is highest s equals minus a. So the point s equals minus a best represents this exponential. That's all this transform tells you. If a is 0, that point is over here. When a is 0, that point is over here. You get a u function. Okay. This is a very quick way to recall what is Laplace transform of e power minus at. Function is most similar at s equals minus a. Function is singular at s equals minus a. So notice, and this is a general function f of t. You're trying to see similarity with e power minus st, right? This e power minus at is most similar when s equals minus a. That is one way to look at it. You could make sense out of this green boxed formula that way. Even otherwise, that is one detail you want to be able to recall. And technically, if you know that, you can also know what is Laplace transform of u of t. So this is the most important formula that we'll need. Now, basic properties, important properties again. Okay. Important properties. It's also sort of most important properties. Important properties. Laplace transform. Some of this we have already seen. This you cannot take this for granted. X of t transforms to x of s. Okay, you always start out with this. So these two are Laplace transform pairs. If you multiply this function by a constant, what does it transform to? The function is multiplied by a constant. Multiplied. What does happens to the transform? A is a constant. This is fairly easy. A x of s. This is now it behaves linearly. No big surprises there. This is also quite useful. Example, if you know Laplace transform of e power minus at, this is 1 by s plus a. Laplace transform of say 2 e power minus at is 2 by s plus a. So for recall purposes, let me quickly do this. So Laplace transform of e power minus 2t power minus 2t transforms to 1 by s plus 2. Notice this blows up at s equals minus 2, that coefficient. Okay. 2, or let's say now 3, to distinguish what is what. 3 e power minus 2t. This transforms to 3 by s plus 2. So one quick question, what does minus 4 e power 5t transform to? That means, this is a double arrow. We can go from this side to that side to this side. What does minus 4 e power 5t transform to? Quickly. Minus 4 by s minus 5. Great. This transforms to, first do e power 5t. E power 5t will be 1 by, when s equals 5, it blows up. It's multiplied by minus 4. Okay. So given this, you can get that. So you can move from this side to that side to this side. Right? So most important formula I have already said. Take two functions. I do a convolution. What is convolution? We'll do tomorrow. Becomes x1 of s, x2 of s. This I have already told you. Convolution becomes a product. Important property. Write down what that is. Convolution becomes a product. Then comes differential equation becomes algebraic equation. Again, your x of t transform to x of s. What does dx by dt, derivative of x, what does this transform? This again, most of you know. And again, this is one of the most important formula that you need to know. Not the nth derivative, right? If not the nth derivative, you need to at least know it for the first derivative. That is very good. Yes, x of s. And technically, there is also a, that integration, you have a plus c on this thing tail hanging around. There is a minus the initial condition. Yes, x of s minus initial condition. Also, the initial condition. Initial condition. Okay, that also shows up. Often this is set to 0. If it is not set to 0, you want to make sure that term shows up. That is initial condition. It is all a differential equation, whatever that. initial value that will show. The first derivative, at least most of you know. We'll learn one more, okay? There are applications, so we are still doing properties, right? We'll do one more property. Important. That let's see if any of you can answer this. Again, our story is this. X of t is to x of s, right? Can anyone tell me what does this function, the function of t, that function is t, function is time itself. What does transform? Anyone know this? No, delta of t, u of t. Delta is a spike, u of t, this is a constant. Now, what happens if it kind of linearly increases? The function is time itself. See, notice t square is a function. Sin t is a function, right? T is a function. That t, what does that transform to? Okay, which is where, the last thing that I'm going to give. If x of t transforms to x of s, you multiply x of t by t, product. Product of t and x of t. This transforms to, it's very similar to this. Derivative transforms to x of s. Now we are asking t x of t. We almost did a ulta of that. Instead of s x of s, we did t x of t. What does this transform to? Not very surprisingly, this is derivative of Laplace transform. Negative sign. You could do, and yeah, again, see, notice any of these things, you could technically go get the answer from this integration. In fact, we are only talking about simple things. You could do the integration, and you could technically get it. You can do integration by parts, isolate or something like that. You can get it, but my thing is, again, the examination, you don't want to spend that time. Okay, so if you can recall the boxed ones, not everything that I wrote. Notice that I haven't boxed a lot. Question I boxed, SS complex that I boxed so far is just like we ranked it. Okay, not a big deal. This is the first major formula I boxed. Multiplied by a constant. Okay, the function transform gets multiplied by a constant. Convolution I boxed. Derivative I boxed. This is the last thing, at least I'll box. Okay, I already told you. So it almost looks like this. Notice looks like we have flipped it, right? We are trying to find what the transform of that, right? T x of t. What is the transform of that? It happens to be a derivative of the Laplace transform x of s. Okay, but with a negative sign. Again, we'll put this equation at the right place. So t x of t transforms to minus, this is derivative of the transform. Of course, it's a function of s, so you can only differentiate with respect to x, and there is a negative. This looks very similar to the converting differential to algebraic equation form, but you are doing it with not with in the time domain, but you are doing that in the frequency domain. Okay, so that negative shows up. So, for example, q of t transforms to 1 over s. T that is equals to t q of t transforms to is nothing but t u of t. U of t is a constant one, right? At least for now, for t greater than 0, t is same as t u of t. So you have a function and you are multiplying that by t. What should it be according to the boxed formula here? So according to this boxed formula, that Laplace transform take its derivative, right? That happens to be minus 1 by s square, derivative of that. Or what is the Laplace transform of t? Let me write this down. Notice this goes to minus d by ds of 1 by s. Negative of derivative of 1 by s. Yes, minus 1 by s square, minus of minus 1 by s square, that equals 1 by s square. So your t transforms to 1 by s square. We just derived it using t x of t transforms to derivative of the Laplace transform. Sense? Formula and application. Something that you don't have to remember. T transforms to 1 by s square, but what all of you should remember is this. This side you got negative of derivative. So instead of for this is the only thing that we are, that's not a convolution, so we'll put it different. This is the only thing technically we are only transform, not properties, only transform that we are recalling. Dagger. This can show up from that, right? This is spike is not that important. I just gave it for completion sake. Spike is not that important. Okay. One formula. Derivative formula. A derivative formula has a minor variant. Okay. This has a variant. Will the variant is written here. So we'll not clutter this page. Again, if you remember this, you can get that. I'm telling you it's a variant because now that's easy to remember. If you know that, you kind of know. There is no initial condition and all that here. And you have to do a change of sign. Quick example is shown here. Okay. A lot to ask, right? 2. Count. 1 e power minus 81 by s plus a. You know the convolution, okay? So this is 2. Differential becomes algebraic. 3. There is a variant, that is 4. Most other things you can technically get it. So 4 so far. I told you 10, right? So let's see if we can make it shorter than 10. So shall we go apply this, then come back here? 2 more properties, or let's finish this. Important. We have seen some examples anyways. So notice t transforms to 1 by s square is an example, right? Important applications. Some fairly very well known things. First one being you can solve differential equations. Second one being transfer function. Of course, if I are trying to solve differential equation, this will show up as transfer function. I'll also show an example of this transfer function. We got 2. Initial value theorem. There is a variant of that. Final value theorem. Anyone know what IVT and FVT are? This is initial value theorem. Initial value theorem. This is final value theorem. I'm sure some of you, at least one of you, know something about this. What are we talking about? You have y of t function. That's Laplace transform. So given this, know the Laplace transform. There are often notice for simple functions like this, you can go this way. 1 over s square, now we can say this is t. For 1 over s, this is u of t, right? Now for for given minus 4 by s minus 5, you can say this is minus 4 e power 5t. So those yellow arrows you can say. Yellow arrow you can quickly say. This yellow arrow you can quickly say. But what if this yellow arrow is very hard? What if this is hard or that is not really necessary? This is like, now to give you analogy, cover everything in the syllabus, cover sufficient to clear or cover sufficient to get all India rank, single digit AIR, right? These are very different things. Cover everything. Okay, that is like, hey, tell me the inverse transform of any y of s. Hey, at least can you tell me some special cases? At least can I get single digit rank? At least single digit rank, sir, some of you are wondering, but at least can I get single digit rank? Right now, this is not, I'm covering syllabus is quite vast. Getting single digit rank is a subset. Okay, that's a simpler problem. Clearing is much more simpler problem. Like that, sometimes this yellow arrow is hard. There are many such y of s in real life. But at least can we say something about y of t? That is the question. That is how this motivation is there. This is hard. At least let's see if we can, if we cannot finish the full thali or the full meals, at least like are there any good things that we can taste and enjoy? So even when that is very hard, things specifically are important. One is in fact a variant of this. It's very easy to find what the initial value is. And y of s. Easy to find initial value. You're not trying to find the entire function y of t. What is the initial value? What am I going to do next month? I do not know that. What am I going to do tonight? That I know. What am I going to do tomorrow morning? That I know. Tomorrow morning I'll wake up. Right? That's easy. What I do tomorrow whole day, that I do not know. Whole month, the next whole month, I do not know. Right? So easy to find the initial value. Even if the entire function is hard to find. And how do you exactly do that? The Laplace transform. Multiply by s. Let's make this typographically better readable. I'm also giving you opportunities to now fill up the detail. Okay. Limit s tending to, trying to find 0, you have to substitute s tending to infinity. So given the function, multiply by s, substitute the limit s tending to infinity, you get the initial value. This is important. I'm going to box that. Easy to find initial value in Laplace transform. Same thing, easy to find the final value given the Laplace transform. A of infinity. There is a color issue. So we'll resolve this color issue with final value theorem. Phi of infinity. We'll give you examples to all of this. To find this, again take the transform, multiply by s. Now we have to substitute s into 0. We put 0 here, get the final value. So let me again put that in simple English. Final or steady state value is easy to find from office. Yeah, great. Yeah, and this is now as I was writing it. So this, in fact, this clean slate, this blackboard is very powerful. Okay, because often what happens is even I do that, but that is for depends, right? Uh, if we have details in the screen or in the PPT, teacher takes those details for granted because the student is trying to catch up with that. But now this gives a level playing field both for the student and the teacher, right? Because as the teacher is writing it, student can catch up. It's not all of a sudden suddenly appearing in the screen. But for that reason, um, I see why that blackboard, or right now we are what we are doing, right? This I'm writing everything from scratch, right? That is very, very powerful. Or in fact, I feel this is very student friendly. This is one box thing. So 6, 4, no. 4, this is the fifth one, sixth one. That's it. Done with basics and most important things of Laplace transform, in which we can answer, likely answer one easy question, have a good chance of answering a moderate question. Okay. So before, while I say that we can answer, let's do let's look at PYQs. I'm not going to solve them, but let's see if the questions are familiar. We deep dived into one question. Let's see if the questions are familiar. The question makes sense. I'll also stop only at easy questions. Okay. It's not Laplace transform, but you will look at the entire list of signals and system. Identify all the even functions here. So we'll skip that for. Let's look at this question. Of S is Laplace transform of x of t. Laplace transform of dx by dt. Initial condition is 0. Can anyone answer this? I didn't share my screen. So the question was not visible. Now all of you are like even odd functions. Which of the following are even odd functions? Can anyone? I'll give you like 30 seconds. Can anyone figure out the odd functions here? P is odd. The sign is odd. Then cos is even. So anything, even into odd will be odd, right? So S is also sin t cos t will also be odd. Even plus odd is neither even nor odd, right? So P and S. Okay, one S and S, easy S and S. Most of you familiar with, great. Even function, I'll skip this for now, okay? Because for focusing elsewhere, x of t is the Laplace transform of the signal. Laplace transform of dx by dt. Assuming x of 0 is option A. Shraddha. A. Quickly, what does option B correspond to? Does anyone know that? This is very good. What does option B correspond to? What does option C correspond to? Option B corresponds to integral. If the derivative gets multiplied, integral gets divided by s. Yeah, that is very good, right? I didn't say that. I was just wondering. That is, say that in today's discussion, wondering if anyone can pick it up, right? Derivative and then you have got an integral. Option C is like, notice if you are taking derivative in the transform domain, that will be Tx of t, negative of Tx of t, right? Option C also we saw today. Option D is slightly complicated, we'll not worry about it. But option C is also we know. Okay. If you can guess B, that is, guess B as in if you can recognize B, that is very good. Like Shraddha did. Okay. 2020, they were warming up. They asked a very easy question. Okay. Now, slightly shift gears. Just tell me, like, I'm not asking you for an option. I'm not asking you for an answer. Asking for a 3-4 word strategy, 3-4 word approach. If you attempt this, if you touch this question in the examination, what would you do? Okay, in 3-4 words. Yeah, 3-4 words doable. Let's say unit step input is applied to a system with impulse response h of s. H of s is given. Output of the system y of t at t is 0 plus s. 4-word strategy or approach. That's all I need. I don't want you to solve this right now. In fact, in this case, the answer is one word. Approach is one word. Yeah, see that part, all of you got it. That is, don't do convolution. Convolution, see, notice I have been avoiding that because now that will all now you'll go into a roller coaster. Okay. So convolution is hard. That is why now Laplace transform makes your life easy. Answer is not one. So fine, you have part of the answer. Input into impulse. Input is step. The Laplace transform of that. Systems Laplace transform is also given, h of s. Okay, they are calling it impulse response. Okay, that is a system's Laplace transform is referred to as impulse. No big deal. Multiply and divide by conjugate. No. What do they want? Do they want the entire function y of t, or do they want something special about y of t? So again, analogy. Now, do you know what you are going to do? The actual sequence of things, the entire day tomorrow. Do you know what you are going to do tomorrow first thing in the morning? First thing when you wake up, right? Or last thing before you go to sleep. Do you know that? Yeah. So one word answer is, again, someone gave that, Mukta gave that. This is initial value theorem, IVT. Yeah, technically, initial value theorem is for 0 plus. You can have a spike at 0. That is, your input can be slightly messy. Let me just tell you why they are differentiating that. You have a sudden change at 0. So distinguish that now. Give me 1 second. Was working all along. Why is now sort of a sudden? Class and all won't get cancelled. I have a backup tablet. Yeah. So just a backup pin solved. So where was I? So they are trying to say 0 plus because they are now trying to differentiate. Hey, now this should work. Just give me 1 second. Okay, so this is called redundancy. And so on, you got 2 eyes, 1 eye, like now dust falls in 1 eye. You can still drive with your second eye, right? Or do important things with this eye. See, this is to differentiate known as the input. The input and to calibrate this. Yeah. Hey. Okay, let's say this function. Okay, looking at x of t. X of t, can be a spike. There can be a sudden jump there and then something follows. This is your delta of t, by the way. It is 0 everywhere, except initially there is a spike. The behavior at 0 plus and at 0 and at 0 minus, slightly to the left, slightly to the right, and slightly exactly at 0, they will be slightly different. We have something like a spike. So to differentiate that, they'll always tell you, hey, we are looking at slightly to the right, or irrespective of sudden changes at even with a step function, you have a sudden change. So irrespective of any sudden changes at 0, tell me what happens at 0 plus. And IVT also applies to that case. Okay, fine. And that is also what I would classify as a slightly that's an important detail, but that is not a basic detail. If you're trying to get an advanced yes and yes question correct, you would need this detail. Okay, let's go to the next one. G of t is df by dt. G of t is a derivative of f. Laplace transform of small f, that is capital F of s, is given. F of s is Laplace transform of the function small f of t. Then the value of g of t at t equals 0. It's not a one-word answer, perhaps 5-6 word answers. IVT is a part of it. You want the initial value of g of t. Can you add something more to it? This initial value theorem plus something else. So apparently I had my second pointer there that was biasing. So that's why I couldn't draw straight lines, I suppose. It was getting two inputs. The pointer location. So I had the other pen nearby. So that was biasing the signal. Anyways, interfering with this input. Okay, let's see where this is. IVT plus what? Probably we should solve this question today. This is IVT plus. In fact, we can also go ahead and solve. I'll do one more thing and we'll go ahead and solve this. It is from one of the things we saw today. F of t goes to f of s. Way to go from here to here, given that this happens to be by dt. Derivative after IVT. No. IVT, you substitute, you take the limit, it's a constant. You cannot take derivative. But the problem is you do not know g of s. You have to technically, your value of g of t, you want a g of 0, right? So you have to apply IVT to g of s. You do not know g of s. Is there a way to know g of s? So what you want is g of 0, IVT to g of s. That is. But right now the problem is, hey, what is this? Oh, you only know f of s. Think about it. Again, it is one of the boxed details I discussed today. If you know the Laplace transform of f, you know the Laplace transform of derivative. Right? Know the Laplace transform of. So you technically know the Laplace transform of the derivative. This will be s f of s, but you have to be careful. Minus of 0. Initial value of f. How do we know that? You have to apply IVT here. Apply IVT to get f of 0. Initial value of f. Whole thing is the g of s for g of t. There you have to apply IVT. Okay. You have to apply IVT twice here. This is your g of s. Apply IVT here. Okay. Whether or not you capture this term will easily let you astray into either infinity minus pi or something like that, something absurd. So you also have to apply IVT twice, not once. You have to apply one property of Laplace transform. So this is somewhat of a hard question with traps. Okay, but fine. At least the question, at least the approach makes sense right now. Yeah, that is correct. If I have to do this, so first of all, you have to find what the g of s is. Your answer is this. Let me write down what the answer. Answer g of 0 is limit s tends to infinity g of s. Find g of s. Okay, question makes sense. Right now, that is my objective, not to solve this. Linearity is number one. This is hard. Region of convergence, left of plane, be too much. Cumulative roots of the characteristic equation of a linear second order physical system match the nature of the roots with the natural response of the system. This is not Laplace transform, but now we are into characteristic equation is denominator of transfer function. But even otherwise, I can suppose characteristic equation. You have done this, right? That is second order systems differential equations. You know how to solve. Guess e power mx m will be solved for the characteristic equation. So m1 m2 are real, you get over damped, right? Equal, critically damped, and then this complex. So this is a simple question that basics of mathematics, basics of yes and us, basics of controls, basics of circuits. Okay, basics. So most of you could answer, I suppose. Directly see. Great. System described by the following differential equation. 0.01 d square y of t dt square, 0.2 dy of t dt plus y of t 6x of t. Where t is in seconds, x of t is unit step input applied at t equals 0. It's a step input. So we have solved differential equations where the side is conveniently was set to 0. Now no. There is an input there. This is like left on your own. How does your learning happen? Now someone, either a friend or a teacher, intervenes. There is input. Okay, now how do you learn? Right? That's a question. In fact, actually, this is the point of teacher is to actually fine tune these parameters for you so that your learning is optimal. But anyways, so The magnitude of the output at t is 1s. Round off the answer to 2 decimal places. How do you find the output? Again, give me a 3-4 word approach. 3-4 words, okay? The second order differential equation. Technically, we do not know to solve this through engineering mathematics. For engineering math, this is hard. So find the output at t equals 1. Yeah, differential equations. Engineering math, this is now a hard problem. So make it an easy problem. Take Laplace transforms, simplify the transform, then do inverse transform, get the solution. For example, you can technically see solving the differential equation, getting the answer, undoing the change. Okay, all of that you can technically see. Solve it using Laplace transform. So slightly time consuming but doable. Okay, so need to know a couple of steps. This is hard time, peak time, twice time, stable second order. Although it says unit step response, the moment it says peak time, this transient second order response is slightly hard, so we'll avoid it. Okay, this question is Laplace transform. Solve the differential equation using Laplace transform. S is j omega. That is your S is sigma plus j omega. Sigma is set to 0. You got the transfer functions. We already did this, right? Second order low pass filter is being constructed by cascading to first order low pass filters. Undamped natural frequency. You have to compare it. I think we did this problem when you did filters. You have to compare it with the standard form. But notice the transfer function, essentially this is coming from Laplace transform. Okay. So notice this is, I'll tell you something at this stage. The transfer function is of the form 1 by 1 plus s by the cutoff, s by the magic frequency. 1 by magic frequency is a time constant. This is of this form, 1 by 1 plus s tau. This is also of that form, 1 by 1 plus s tau. 2 tau 1. 1 by omega 1 is tau 1. Okay. So omega 1 will be 1 by RC. 1 will be RC. Time constant will be RC. Okay, but look at the term 1 by S by 1 plus S tau. Okay. Fine. This we'll discuss this in filters. Okay, from here on there will be convolution. Okay, discrete convolution fairly easy. Discrete correlation, cross correlation, all of that is fairly easy. We'll do this tomorrow. Nyquist and basic discretization. So Nyquist and convolution we'll do tomorrow. Technically, this is also a Laplace transform, or actually simpler than that. Okay. Fine. Remember, we deep dived into this. Now, if you go at the notes, it should be fairly easy how we did this. Instead of giving the mathematical function of the transfer function, they gave it pictorially. What is the amplitude response? What is the frequency response? From that, you have to infer parameters, specifically what is the decay constant. Is that 1 by 1 plus s tau? The time constant shows up in the transfer function. So you have to infer what the time constant is. Once you know the time constant, the solution is fairly simple. Okay. So now these are all things that get harder. Okay, but the point is, these are at least moderate questions. Any wishes? You solve questions like this. Second order low pass filter, high pass filter, band pass, all pass. Question like this shows up, you should be able to solve. This is doable. It will take you about 10 minutes. This is doable. If it's a 2-mark question, that 2-mark, the later half of the exam is actually well worth it. This is doable. Okay. If given you don't, you are quick with match steps, your foot. Okay, know the depth before before putting your foot or before stepping on the lake, right? Know the depth, right? So this is mathematically quite involved. A question like this. So you're getting in, make sure that you're quick and familiar with the steps. Okay. This all of you could answer. This is also a question like this. The moment it's not just IVT. This is IVT plus this property plus that. Should be a word of caution. Okay, this question on an average, I'll skip at the first pass. I recognize IVT, but still I'll skip at the first pass because IVT plus one property of Laplace transform. Last 30 minutes, perhaps nothing else to do. I'll do this. This I will do. I can quickly see this is IVT. All of you could do. Initial value theorem. Questions don't get easier than this. Fine. So objective is the easy questions answer. 9:40. So now I'll come back and I'll solve you this question. I'll solve you 3 questions for today. Questions are quite involving, but come back and solve this. But let's learn few details. Okay, there is one step you need to know. At least let's look at that step and then solve those questions. We did a deep dive of this problem yesterday. We looked at many concepts we learned today. Right, a convolution becomes a product, and then one u of t is 1 over s, e power minus at is 1 by s plus a. So all of this. So the question they gave it as a figure. We figured out the transfer function. All pass filter has to be a minus s by a plus s. I suppose input is step, so you get 1 by s into transfer function. Output is 1 by s into a minus s by a plus s. I said, okay, notice, see, taking Laplace transform of this input into the transfer function. Output is input into transfer function. That is what I have written now. But this step, to find, we have to find y of s. So that at what time does the output become 0? That's what we want to do. So we have to find y of t. This is not initial value or final value. To know the function so that you can find when the function becomes 0. But hey, how do we take inverse of this? How do you take inverse Laplace transform of this? Is 1 by s, a minus s by a plus s. It's not a simple thing. Taking this inverse is a very important step that often is in the way. Okay, and notice I did it like this. See, with some footwork, there will be 1 by s into minus 2 into 1 by s plus a. So you can verify if you add these two things, you will get this. You can do that verification. But how do we go from there? I put footwork here, but it goes by the name method of partial fractions. You are trying to find split this. Okay, method of partial fractions is somewhat uh, you know often the names itself will like suddenly capable of secreting cortisol and things like that, right? So we'll call it divide and conquer. Okay. Method of partial fractions, also known as divide and conquer, this is useful for doing inverse Laplace transform. So example, find suppose the function we had as 1 by s a minus s by a plus s. Okay. So notice 1 by s into a minus s by a plus s. Right? Technically, plus s into a plus s. Which power of s is higher? Is it higher in the numerator or is it in the denominator? Is this high in the numerator or is it of s? Denominator is s square. There is a numerator of s. There is a denominator of s. Okay. So typically, your order of numerator of s less than denominator of s. Denominator has a higher power of s. That is very typical. Yeah. Okay. Most of the problems you will come across will be of that form. And notice there is a mild detail. Something called zeros. The roots of numerator. What we call as zeros. Then we have poles or singularities, the roots of denominator. This is for a transfer function, but for any function you can technically say this. Okay, so you can try to do like add plus yes, subtract minus yes, something like that. You can yes minus yes, right? You can try that and see if things simplify and all that, but there is always a systematic approach. Okay, and that is, let's take this. I noted this. That is greater than order of d of s. Okay, whenever this is the case, you can do this. Do the following: a minus s by s into a plus s equals the first pole. So I'm going to highlight this. Yeah, let's highlight this. That's the first pole, and then you have the second pole. First pole, second pole. All right. I'm always going to write this as some constant by s, some other constant by s plus a. I just wrote it as each pole separately. Color coded it. See, the as far as the order of the numerator is higher, the power of s is greater than denominator, I don't have to worry about this term, because when you add it, this will go here, this will go there, and then somehow the s will show up in the numerator. I just taken the poles and I have written it this way. And this is also technically you can write this in be your constants. So the point being, no, notice I have divided that. This is easy to hard to take Laplace transform. T inverse is hard. T inverse is easy. You know, this is u of s, u of t. This is e power minus at. You know that. What we mean by divide and conquer. Now divided, if divided, easily conquerable. The question is if. That means if you know these constants a and b, you have divided them successfully. A and b constants. They are not functions of s. They are constants. Can somehow find them. We have divided them. Each part we know how to take the Laplace transform. Yes, we know the Laplace transform of this. We know the Laplace transform of this. Anyone suggest me? I'll give you 2 minutes to think. How do we find this constant? Can anyone suggest me approach? It's somewhat systematic. This way of doing it is systematic. There is no guessing this, that, and all that. Can you find the constant? And what we are, so this is, now we are splitting into fractions, partial fractions. Okay, that is why this goes by the name method of partial fractions. So find a. Take LCM of denominator. Yeah, okay, fine. Then compare coefficients. You could do that. Let's call this f of s. You know, I don't know how many of you remember the trick used to find coefficients of Taylor series. We wanted to isolate one coefficient at a time, either by differentiating or setting a specific value, or differentiating and setting a value, something like that. We used a trick. We are going to do the same trick right now. A, the function, remove the singularity, evaluate it at the singularity. Let me put this in English. Remove singularity. Then once you remove the singularity, you can evaluate. Yeah, no, Shraddha is saying a coefficient of A is put 1 by S, put S is 0 in place of coefficient B. Yeah, so remove singularity, evaluate it at singularity. Okay. So this is take this function. This is a function f of s. Remove the singularity. Okay. Now evaluate it. Now we can substitute s is 0. What do you get for A? If you substitute s is 0, that is fairly simple. So substitute s is 0, 0. What do you get? A by A, get a 1. You got your first coefficient. Great. So same thing. Remove singularity, evaluate singularity. Taylor series also we did the same thing. Okay. Shraddha is very close, but do this should be done. Find B. Let me write down what that equation is for reference. We have to find the B. Yeah, which will be A. Okay, find the B. So I also given, so we don't have to go back there, right? So I given it here. Same idea. Remove singularity. Evaluate singularity. Let's also call it this, that we can see what we are doing. So students know Laplace transform. Students just doesn't know this intermediate step. Taking partial fractions is where the problem. Any differential equations, any of that is lost. The function, remove the singularity. Singularity is A plus S. Evaluate it at the singularity. A is 1 by A. Is it? That is S is 0. Let me see. Remove the singularity. Now evaluate that at S equals minus A. How much is this? Oh, number, okay. Not a number. Give me what this is. Minus this A. The denominator is minus A. Numerator is A. Minus. Notice there I multiplied by S and evaluated at 0. Here I multiplied by A plus S and evaluated at S is minus A. If you look at it that way, it will be confusing. No, there I removed the singularity, evaluated at the singularity. Here also I removed the singularity, evaluated at the singularity. If you look at it that way, we are doing the same thing. There, why you did that? Then substitute there. Here, why you did this? Right? It's a very common question. I'm removing the singularity, evaluating at singularity. That's it. Now we have found the constants. Now we are ready to conquer it. So A minus S by S into A plus S happens to be 1 by S minus 2 by S plus A. Technically, this is Y of S. Okay. Therefore, your Y of t is the inverse Laplace transform. This transforms to U of t, that is 1. I'm going to know this is all t greater than 0. This is 1, okay, minus the Laplace transform of that. This transforms to e power minus a t. Now you got your function. You can see when this function becomes 0. You also know the parameter in that problem, but here this is a subpart. What we did, this divide and conquering. So let me write this explicitly. So we have divided and conquered. Divided, now conquered. So notice we solved a differential equation technically, because the transfer function. So technically, you know the differential equation. One homework could be, so input x of t is 1 by s. Transfer function is a minus s by a plus s. So what kind of a differential equation is that? Okay, try to do that. Okay, transfer function is that. So you could try to do that. Okay, but we have actually solved differential equation. Okay, now let's go back. Let me quickly solve some of these questions. Okay, we last time we looked at it. Can you understand the question? Now we have to solve. There are two major questions, and we got 20 minutes. Let me go solve them. And I'm going to slightly shift gears right now and help me any steps and all that. if necessary. In chat, yeah. So this is odd, even, plus even. That is neither odd into even, odd. So P, yes, C. Okay. Is odd into even, even by odd, corresponds to odd into even, odd, odd. What goes in? Always, always, no, this is always optimistic. What goes in is always positive. Super positive. Goes in is positive. Only positive news goes in. So this is even same thing, always positive. Always optimistic news goes in. Okay. Goes in. For this derivative, this is the option. This is integral of x of t dt. Here, that transforms to dx of t. That should transform to dx by ds. This is something weird, okay? But there goes your answer. Your this becomes 1 by s plus 0, 1 by s. So your y of s is x of s, h of s. That happens to be 1 by s into 1 minus s by wz by 1 plus s by wp. There we found y of s. We want this system output IVT. At least can we find the some of you might be wondering, with the steps. So let's do the step. Really, this is limit s tending to infinity, s into 1 by s into 1 minus s by omega z by 1 plus s by omega p. Yes, this s cancels. If we apply the limit, what happens? So the way you have to deal with this is to pull out the s. Pulling out the s, and then I am cancelling that. Here s tending to 1 by s is, s tending to infinity, 1 by s is 0. There I get, after cancellation, wp will go to the numerator by wc. Okay. So see how I pulled out that s. Okay, this is minus WP by WC. That is your application of initial value theory. Try this step, okay? As in like redo. Say try, sir. Difficult steps, you will leave it to us. Redo. So I also need to find out what this is. Okay, let's do that. F of 0, limit s tending to infinity, yes, f of s. Happens to be square plus s by, I'm multiplying s into 1 plus s, s square plus 12s plus 32. So this is tending to infinity. This term dominates. This has a coefficient of 1. This has a coefficient of 1. That is what dominates. Okay. So this limit, again, if you can pull out s square, you want. But the answer here is going to be 1 by 1 plus 1. Okay. So then goes my next step. My g of s, that is s f of s minus f of 0, and that happens to be s square plus s by square plus 12s plus 32 minus 1. This simplifies to your g of s as, if this goes, I suppose this is s square will cancel, s minus 12s, that will be minus 11s minus 32. Okay, that divided by the same denominator, that is s square plus 12s plus 32. Okay, got you g of s. Same question. Great. So now I got you g of s. Can you tell me the g of 0? Anyone give me g of 0? This is limit tending to infinity. Yes, g of s equals yes. Okay, into that term. Actually, let me simplify this, right? Okay, minus 11s square minus 32 by square plus 12s plus 32, just tending to 0. Because there is a s here and then there is a g of s. Tending to infinity. So the way I do that is, notice this, these two coefficients will be the answer ratio of these two coefficients. 11 there, there is a 1 there. A proper way to do this is this: pull out the s square. Okay, pull out the s square. When you apply the limit, number, the s square will cancel. When you apply the substitute the limit, this term is 0. 1 by s square is 1 by infinity square is 0. 1 by infinity square is 0. 1 by infinity square is 0. So what technically shows up is the coefficients, ratio of the coefficients of s square term. So there will be a 11 that shows up, there is a 1 that shows up. These two gets cancelled. Pulled out the s square and I cancel that. Okay, that happens to be That is your answer. If you do it like this 2 marks is easily gettable in the exam. And if you take like 2-3 minutes to strategize, understand that question, 4 minutes to actually solve this, okay, in the exam you can get this. It's a moderate question. Okay, moderate to hard. This is hard. Let's skip that. Over critical and so PL and QK. See, picture of the roads again is fairly easy. This is the last question that we'll do for that day. Strategy. Approach. Use Laplace transform. If you take Laplace transform of this, okay, so 0.01 square y of s. Now, technically, they should have given you why not and all that. They didn't give anything. You don't bother about it. Initial slope and all that set to 0. Okay, technically that is not good. Y of s, y of s is 6 x of s. Substeps. Can you actually tell me what the transfer function is? Not required, but can you write down the transfer function? Can all of you? Let me write that as a side step. Okay, this is not part of the solution, but notice. Note transfer function t of s okay. Oh, this this point and all that is somewhat not convenient to work with, but let's retain that for now. Okay, this is your transfer function, and you multiply and divide. Yeah, if you multiply and divide by 100, it will be gets easier. We'll do that in the next step. We'll actually, in fact, do that whenever that demands it. So notice this is you got x of s is step, so this is 1 by s. Okay. Your y of s 1 by s 6 by 0.01 s square plus 0.2 s plus 1. Yeah, this is partly finding the roots is hard. So I'm going to multiply that by 100. Okay, so this is into 100 by 100, because notice then it's s square, finding the roots at least becomes fairly easy. Okay, for that reason I did that. So now the question is, if you can find y of t, you can at least find the y of 1. Okay, so yeah, this is may not fit in a paper. By square plus 20s plus 100. This is 600 by s into 10 square plus 10 whole square. They put a curve ball. So quadratic denominator. So technically we do not know how to do divide and conquer this. It's going to be of this form. First order pole, second order pole. See, notice I am over 2 pages of scratch work. Technically, this question is there. I would have got some space. I'm also somewhat repeating, but I am over 2 pages of scratch sheet. So if I am not answering this in other lines, I am skipping this question and moving on the actual examination. Where I notice, this is where I stop and think for a moment. I am running out of scratch sheet. This is going to be e power minus 10t. This is going to be t e power. I didn't solve for b. Okay. Didn't solve for c. But it's going to be, it's 1 by s plus 10 whole square. I know this is a t into e power minus 10t. Formula we did. Then find bc. But there I noticed something. E power minus 10t equals 1. Calculate how much this is e power minus 10. So I noticed the time constant is actually 0.1, or the decay constant is minus 10. Find b and c. Decay constant is minus 10. I noticed that. Calculate e power 0.00004539. Okay, someone did it. Let's make sure that is correct. E power minus 10. Yeah, 4.539 into 10 power minus 5. Yeah, that is correct. So changes is happening starting with 5th decimal place. Rounded off to 2 decimal place. BC, looking at this expression, perhaps it's order of 100. Looking at 600, BC is order of 100. So 100 into 5th decimal place is still in 3rd or 4th decimal. Okay, at this stage, because I'm running out of scratch sheet, the time constants involved are like now. This is a very, very fast decay. E power minus 10t. It's as fast as it could get. 1 second is the normal. E power minus t normally happens. You get some value. For minus 10t in 1 second is like now nothing is there. So I make a very sensible examination. Set this to approximately 0. Set this to approximately 0, irrespective of B and C is. Now my task is to find that A. If I find A, I am done. Because your y of t is A u of t. 1 by s. Just A u of t. So what is the value of A? That is the value of put at t equals 1 second. If you want, you can put a u of t is 1. So I know I can find A in 1 second. How do I do that? Remove the singularity, okay, and evaluate the singularity. That I can do it in one step. So here, remove the singularity. 600 by s plus 10 whole square, evaluate it at the singularity. Evaluated at 0. What is that? Tell me A. Singularity, evaluated at singularity. You can do it with this. Here, remove singularity, that is yes, and then evaluated at singularity. Tell me the value of A. Do that in the tissue paper. Square evaluated at 0. Singularity gone. Substitute S is 0. This is 100 square, 6 by 100. So A is this. Things were actually going out of control, but I had to take a step back. Think of it like not like a mathematician. So till here I was thinking doing it as a mathematician. Thought of it as an engineer. What is the meaning of that? This is very, very fast decay. For minus 10t, fifth decimal place, approximately 0. So what is this A? That is 6. Here I would go answer. It's a NAT at the worst case scenario. You could even call this. It's actually, I'm not guessing. I'm technically that those two. This is actually, in fact, this is the answer. You could go try to find the B and C. Okay, but that would technically be based on those. Those are your decimal place and your beyond the error there is smaller than the approximation that you're looking for. Rounded off to 2 decimal place. The error is in the 5th decimal place. Forget it. Okay? So there I got answer. And actually, technically, from the if I look at it as even as a mathematician, time constant is 0.1, 1 over 10. Okay. Time constant is 0.1. Decay constant is e power minus 10t, minus 10. Very, very fast decay. So there aren't going to be any transient effects. What I learned today, I will not remember 10 months down the line. Perhaps 1 month down the line, I will remember. If I recall it, I will do active recall. Perhaps there are good chances of recalling it. But 10 months down the line, that is what this problem is saying. The time constant is 0.1. So after 1 second, 10 times the time constant, nothing should be there. No transients. System doesn't remember that. It just gives you the steady state. That is also an engineer's, actually a correct way to answer this question. So this is hard, but I could have technically answered it. I could have at least made a very good guess. And then this is a hard. We did a deep dive and I also showed you parts of it. Now this is technically doable in this spreadsheet. Okay. Redo. This is redo here. Scratch it. Don't go beyond this page. It is doable. Okay. Okay. So scheduled time 8:30. Laplace transform. That means 50-60% of signals and systems and a lot of transfer function is done. We didn't look at controls, but yes and S questions should be. Laplace transform is at the core of both S and S and controls. Okay, so here you can make sense out of it, and with practice you can also start solving things. Okay, tomorrow we'll do convolution. This discrete convolution we'll do convolution correlation, and then we'll try to grab convolution. Now discrete convolution we'll do Nyquist. With those two we will grab rest of the other 30% or something like that. Okay,